Hello, everyone. Thanks for being here. It's always an honor and a pleasure to be on stage at Berlin Buzzword. So in today's talk, Radu and I are going to share an interesting use case with you. We walk through how we moved from basic lexical techniques like fuzziness and stemming to phonetic algorithms in order to search names into across a massive collection. But before we start, some presentation. I'm Pietro with my colleague Radu. I'm software engineer at Adeline and open search ambassador since a few months. And my colleague Radu is solution architect. Some words about Adeline. We are search experts. We are integrators of Elasticsearch, OpenSearch, and Solar, consulting and training providers, and we also develop our own solution for e-commerce and enterprise search. And we love to be at Berlin Buzzword and have conferences. So, all right, enough about us. Let's go back to the main topic. Just to give you some background, the core challenge of our use case was being able to match names reliably across a massive data set that is the one of the French National Audiovisual Archives. So the goal of the archives is to preserve the audiovisual heritage. So we have really everything. We have classic TV broadcast, we have YouTube videos, we have podcast tweets, everything. And our job is to make all this, all the metadata behind the content, searchable. So the challenge and the question here is, how do we reliably search through this massive data set for historical figures, actors, athletes, journalists, knowing that the user generally is going to misspell certain names. Now, this happens really often in French because there are many different words and sounds that are written differently, but they sound just the same. And it's really easy to misspell names. My name is 4 letters, and it's always misspelled. So how did we do that?
Yeah, right. So let me give you the incentive and our motivation that had led us to explore and to understand the phonetic algorithm. And everything started from the evaluation of the search engine, the relevancy evaluation of the search engine. We went through different steps, starting from the trivial, naive, it looks good to me, passing through different other steps of precision at K, NDCG, A/B testing, you name it. So we had quite a lot of interaction with our stakeholders, with archivists and documentalists, and in general, the feedback was good. But somehow we kind of had the feeling that sometimes they had some negative feedback, some examples that they could not really explain, and but it was difficult to put in figures or in tests or to show. So what we did, we organized several workshops. We took examples and we tried to understand what's going on. So I like this example because it was something that was coming up in the use case of the archivists, because they organize different studies and they focus on different personalities, different events, and at some point they were confused because they were looking for Mitterrand, the French president between 1981 and 1995, and the results were quite good, but they were swamped in lots of other results, and they were wondering what can we do to improve that. So what we did, a simple analysis of these two words. So I put it here in in French, the spelling of Mediterranean Sea, with some accents on some characters, some double R, double E's. The same for the name of the president. There are the double T, double R. Sometimes people are not very sure how to spell it, so you can have spelling mistakes. You can have, and a simple analyze on the stemmer that we used with the French analyzer showed that the tokens are quite similar. So if you look here, the results of the token is Mediterranean. So with the Levenstein distance of 2, you can easily switch from one to the other. And of course, in the overall configuration of the search engine, we use the French analyzer, and we added also the fuzziness. So actually, the result of these particular queries were very confusing because the amount of noise was really a lot. So we were thinking we should do something, and what if we would change completely the direction instead of trying to improve? And of course, you can have different solutions to put some boosts, to have several queries, and to reorganize, reshuffle the results. But then we are thinking, what if we would go directly to a different method? So why not try the phonetic search as a complementary method? So not to replace completely, but to add some more precision in these specific cases of patronymic, toponymic, lexical search, and give a second analysis on the search. And also, the goal and our bet on this choice was to rebalance the core trade-off in between precision and recall, to make sure that enlarging the recall of our queries won't be in the detriment of the precision, and to reduce this way the noise of the answers. So we were using stemming, fuzziness. It worked fine. It doesn't come as a surprise. The language in our data set is mostly French. It's also a bit of English, but mostly French. And in general, it works quite fine. But in this specific case of patronymic and toponymical queries, it needs some improvement. And then we are trying to get our information and to study a bit the subject. I won't get here into details to give you a full history of phonetic analyzers, because it's a very interesting story. But what was very fascinating when I discovered is that the subject was studied a long time ago. Actually, they started more than 100 years ago with the first algorithm that was based on phonetics. In 1918, 1922 was the first patterned algorithm of Robert Russell and Margaret King Odell. They were using that in the public administration to arrange physical cabinets, and they realized that trying to understand the pronunciation of the words and to organize the data and their indices according to the pronunciation could greatly help in their job. So that was even before the implementation of the algorithms in computer science and so on. Then we had different variation of and improvements of the algorithms. I just mentioned all of them, but just stepping directly to the modern history, let's say, the first Java library implementing different algorithms arrived at around 2003 under Apache Commons codec. And since 2012, for instance, in Elasticsearch, we have a phonetic plugin that actually integrates this Java library, and it was maintained over the time up to the latest version of the search engine. So it's a long history of these algorithms, we were not trying, and we didn't have the objective to reinvent the wheel or to improve the algorithms, because they were well studied along the time. But what it's interesting for us, it was interesting and challenging to see how we can use them in our purpose. So how it works? How does it work in the phonetical analysis, for those of you that you are not familiar with that? So the phonetic search works by creating and generating canonical hashes of each word. And it's really straightforward. 3 steps of this short analysis. First of all, you do a certain normalization to remove special characters and accents, or to clean the input. And the second part is the most important, is the encoding. Basically, you associate a code to each word, based on some specific phonetic rules, and we'll go a bit deeper in understanding these rules in the next couple of slides. So then the last step is to index these codes, and then you can do the matching of your queries based on this exact matching based on these codes. This is a whole theory that we discovered, and we learned lots of things about how the phonetic rules are generally defined and what's the base of these methods. So everything is around what we call the place of articulation. So different sounds, different consonants can be regrouped according to the position of their where they are pronounced in our vocal tract. In the higher part or the lower part, or so for instance, all the B, F, P, V's are grouped more or less to the same area. So that leads to a certain conclusion that even in different words, if they appear in different parts of the word, they can be almost considered equivalent. And another rule is that the vowels are ignored. And here I mentioned SoundX. I use it as illustrator because it's the first algorithm, but also the simplest. So our point was not to try to understand the very latest algorithm or to go in the very specific details, but just to have the comprehension of this, the functioning and the method. So the SoundX algorithm is very simple, as described here in these 4 simple steps. We keep the first letter of the word. For the coding, we associate a number from 1 to 6, and again, these consonants are grouped based on point of their articulation. Third step is the deduplication. So if you have a sequence of the same group of consonants, you just keep one, and you keep the code short at three numbers. In our Mitterrand examples, the first step, so we keep the M, then we have 2 times the 3 that corresponds to the T, and then 2 times 6, 5, 3, and next step we reduce the double numbers, and we get to 3, 6, 5, 3, and at the end we get a simple code M365. Very simple, right? So, but what's the problem? What's the catch with that? There is no universal solution. Here it was an example of a simple name in a specific language. They won't function in the same manner in different other languages. So the different implementations of the algorithms, they have to take into account the specificity of the language, and that's why you have several versions, several flavors of different algorithms. You have SoundX in English, metaphone, double metaphone, and so on, as we were concentrated on the French one. This is just some small details about the French use case because we have some specific particularities. We have silent terminations, nasal vowels, and homophones. And we got the chance to benchmark this difference algorithm.
Yeah, thank you, Radu. So as you saw, there are different algorithms. So you may be wondering, how did we pick the correct one for our French use case? So we did some benchmarking. What we did was putting together a testing corpus of French homophones. So that there are words that are written differently, but they are pronounced in the same way. We included everything from everyday object to people and city or region names. And if you know anything about the French language, there are tons of them. Like I was just talking about this yesterday. As an example, there is Margot that can be spelled in at least 2 different ways, but people, I think there are even more than 2 different ways. So our goal is just straightforward. We run every algorithm against this data set to measure the percentage of homophones pairs that correctly mapped to the exact same phonetic token. So, for example, for Margot, we were expecting to receive the same phonetic token, despite the fact that it's spelled in different ways. And the result showed that the French specific algorithm, they perform better, like the phonetic Berger algorithm. And so we decided to go for it. Now, if you are familiar with Elasticsearch or OpenSearch, you know that to use a phonetic algorithm, you need to install a plugin. It doesn't come out of the box. But once you've done it, and it's really straightforward to do it, you can just use the phonetic filter just as any other filter. So it's really easy to use. Now, the problem is that the Analysis Phonetic plugin implements the Apache Common Codex, and not all the algorithms are implemented there. The Berger algorithm is not even implemented in Java. I think it's implemented in PHP, if I'm not wrong. So there were 2 different solutions. One was to build our own custom plugin, so we had to develop it. And the other one was to develop an external service that we could use at search and indexation time. Now, a pro tip with something nice that I like with OpenSearch is that you can integrate your external service through connector and integrate them into your workflow at indexation time with the ingest pipeline and at search time with the search pipeline. So it was really easy to integrate, and we went for the second solution. Other few things that we did was double or multiple field strategy. So we indexed the same field in multiple format. Of course, we added some boost for exact merge and for a match and for a phonetic match. And another suggestion, as performance they differ if you're using a language or another, was to work on routing the language. So pick the language and the phonetic algorithm that goes with it. And absolutely something that we do not recommend is to apply fuzziness to phonetic keys. Now, to conclude, we didn't have much of AI here. All the algorithms you see is just simple substitution, essentially. It's insane, but they work. I mean, there are also some works that have been done about machine learning, the Chi2P model, graphene to phoneme models that can create the phonetic representation of word. And I found out there is also this nice study about how a large language model can give context to phonetic algorithm, because apparently in some languages, just some words, they have the same spelling and different pronunciation based on the context.
Yeah, so let's wrap up our story about phonetic search. I hope we caught your attention and give you psych to go and look and explore this interesting field. We just had a bit of time to scratch the surface of the subject. But it would be to remember three things from our discovery and our work would be to consider it as an option, as a complementary method to the lexical analysis. So don't base everything exclusively on phonetic analysis. The second point is it really depends on the language, so take that into account and apply it to your specific language and the specificity of your data set. And the last point is we don't have a general solution. That's why we tried several algorithms. We tried all of them that we could, and it really depends on the one that best suits your specificity, your use case, and that has the best performance on that. You cannot expect that in advance. You just have to try, and that's what we did. That's our conclusion. Everything is based on testing and continuously evaluation of different options. So thank you for your attention. We are here to take some questions if you want, or to keep in touch if the subjects interest you. Thank you.
Thank you, Pietro and Radu. Unfortunately, we don't have time for questions now, but I'm sure they will be around and you can approach them anytime. Thank you.
Thank you.